Welcome. Today we're going to be talking about genetic algorithms, and I want to make sure I call out here this is an introduction, so there's lots more stuff than what we're going to cover here today. But the goal here, what I'm hoping to do is whether you're a developer or someone that works with developers, even if you're not writing code yourself, I hope to give you a good overview of what genetic algorithms, how they work, so you can participate in conversations. So even if you're not responsible for writing code, if people start talking about this, you'll have an idea of what they're talking about, where it's going, how kind of the process works. Another thing that I think will be useful about this is if you start looking at how machine learning is done, and particularly from that moving on into some more advanced AI, I think a lot of the terms that we look at in genetic algorithms provide a really good foundation for understanding how the machine learning piece of things work. I was working through a machine learning book here a few months ago, and which was one of the things that made me want to do this talk, because I'd like to do a talk on machine learning, but I think this provides a really good kind of foundation for kind of understanding some of the terms. So that's why we're here, where we're headed with it. Hopefully that's of interest to people. Let's look at what we've got coming up in the next few weeks. Next week, we've got George Dinwiddie is going to be talking to us. He's going to give a talk. So your manager asks you for an estimate. Hopefully that's an interesting topic. I know a lot of people, I've worked with a lot of teams that get in this situation. It's like, we don't really know. We know there's a lot of unknowns, but I'm being asked for an estimate. And once I give that, that's going to go on the project plan, and it will be, everybody's going to be held to it. So he's going to be talking about that. So I'm looking forward to this talk. It's going to be a lot of fun. When you get this invite, if there's people you know that would benefit from it, that maybe don't usually come to the Lunch and Learns, please feel free to forward the invite to them. They are forwardable, so you can send them on to other people. After that, we're going to be doing Agile Principle number 8. We've got a new cartoon, and we're going to be talking about sustainable development, so that's going to be fun. And then the week after that, Alec Bird is going to be talking to us about how do you become an expert when you're on the clock. And he's structuring this to kind of in two parts, where he's going to have one part where he kind of talks about things in theory that should be applicable to everyone. And then the second part, he's going to actually get into some code and demonstrate stuff. So there'll be some code in here, but even if you're not really into the code, the first half may be pretty interesting to you, just about how do you develop skills when working in technology. And then 2 weeks after that, we've got Mike Clement is going to be coming and talking to us about focus on flow, lean principles in action. When we sent out the poll asking what people were interested in, lean was a big area that people were wanting to know more about. So this is part of the response to that. So when we get through with this talk, if there's other things related to lean that you want to hear more about, let me know, and we'll look at doing that. But for today, we're talking about genetic algorithms. So what we're going to do first is go through and talk through some of the vocab, just so we understand what we're talking about. Then we're going to do a really simple example, and then look at a place where that was actually done in the real world. Then we're going to hear a word from our sponsors, me. And then we're going to go on and look at this example right up here, where I went ahead and built my own genetic algorithm to try to draw a picture of Abraham Lincoln. We'll look at how that works and how it evolved over time. Okay, so first word we want to become familiar with is chromosome. And forgive me, sometimes I've seen genetic algorithms refer to these as different things. Like sometimes they refer to this as DNA. In biology, if I understand correct, you have the idea of a chromosome, which is made up of genes, which is made up of DNA, which type of acid. So you kind of got that structure. Oftentimes, though, I think we refer to a strand of DNA and refer to a gene, or maybe an entire chromosome, because a chromosome is a really long strand of DNA. And feel free, if I get any of this biology wrong, feel free to correct me in the comments, so we're all straight on it. But what we're going to be calling a chromosome for this is it represents a proposed solution. It's a representation of a proposed solution. So it's some way, if you think of a DNA, like your full genetic code as DNA that represents you as a person. So in this case, we're going to be dealing with much smaller things rather than trying to create a person. We're not doing any Frankenstein stuff here. But we're going to have some way of representing a proposed solution. And if we're representing it in computers, we may represent it as bits. It could even be implemented as a bit stream, just a bunch of ones and zeros. In the situations we're looking at, we're going to be representing it as numbers. But as we look at some of the other definitions, you'll see why those might be good solutions so we can mutate them and do different things to them. So chromosome, it's a representation of a proposed solution. The next piece of vocab that we kind of want to think about is fitness. So we have a proposed solution, but we need some way of saying how fit is this solution? And so we usually have some type of fitness function that we can give it a chromosome or a proposed solution and get some type of measurement back that says, how close is this to what I consider to be either an optimal solution, or maybe I don't even know if there's an optimal solution, but how is this solution better than another? If I have to choose between these, how would I measure them? And so there's some concept of a fitness function that does that. Now, these can be very, very complex, dealing with creating physics simulations and doing different things, which we'll talk a little bit on an example of that. But the key takeaway here is making sure that you're thinking in terms of, we have to have some way that something we can do to a chromosome to say, how fit is this for its purpose? So fitness measure is a measure of how good a proposed solution is. Then we have some type of genetic operator. So a genetic operator is going to be ways to modify the chromosome. So one way would be random mutation. Like we're going to go through and we've got a bunch of numbers and we're going to go through and flip some of the bits or change some of the numbers just a little bit. If you think about the idea of how what we inherit from our parents comes from both parents, but then we may also have some mutations. We have something that our parents don't have. And they're not always good things. My grandma was born without a hand, so that was a mutation where some bits got flipped in her DNA that did not that were not advantageous to her. Although she's amazing, she can drive a standard even with it and do all kinds of, and even knit and stuff like that. So she's an amazing person. But the idea that there's genetics there, that something mutated in a way that wasn't desirable. But the genetic operators, what we're wanting to do is a way to modify the chromosome to do different things. So it could be a matter of mutating the chromosomes. It could be a matter of adding new information to the end of it, like extending it. Maybe we add some random information to the end of it and see if it makes for a better fitness function. It could be a matter, the genetic operator could be taking two chromosomes that are pretty good and trying to find some way of combining them. So we hopefully get the best traits from both of them. Maybe we combine them in different ways or randomly combine them. So those are the types of things, just different ways we can modify the chromosome and then measure its fitness and see if it's better or worse than what we had before. Another term, population. So population is a set of solution candidates, usually represented as unique chromosomes. So the idea, if we're dealing with, and most of the examples I'm going to be talking to you, we're dealing with usually with just a population of two at a time, right? I've got the previous thing that I did, and I've got a new iteration. I've got a population of two, and I'm going to take whatever the best one is from that, throw the other one away. But we could have a population that looks very, very different, where we're creating maybe 10 different, maybe we're farming this out to a big computer cluster, and we're creating, each of the cluster works and then gives us back its best one, and we end up with 10 or 100 different proposed solutions of varying degrees of fitness, but that could be the population. And then we might look for ways to take the best ones and combine them in different ways. But just the important thing here is just a population represents a set of chromosomes or a set of solution candidates. Okay, so let's try it. And we're going to go through a very, very simple example of this and then show how it could play out and how it has played out in the real world. Everything that we're doing is going to be very, very simple with just a few numbers, but keep in mind, everything we're doing with maybe 4 numbers could be 400 numbers. So don't let the simpleness of it make you see it as being limited in what you could actually do with it. Okay, so let's say we need to optimize an antenna wire. Like, what's the best shape for an antenna? And so if we assume we're doing that, we need some way of being able to represent what this antenna would look like. So in our case, we're going to just do this in 2 dimensions just because it's easier to draw on 2 dimensions. We're just going to represent it as an angle and a distance, right? If I've got an angle and a distance followed by an angle and distance and any number of those, I can draw a 2-dimensional line that has a different shape. So for example, let's say we start with just random here, and we've got angle, distance, every other one. So these pairs of numbers, and we've got an angle of 90 degrees followed by a distance of, we'll say 5 inches, followed by an angle of 45 degrees, followed by a distance of 2 inches. So I can do that, and I know 90 degrees would be up, but I'm going to do it sideways with my protractor here just so it fits on the screen. So I'm going to draw a line that's 5 inches long at 90 degrees. So I go over like that, and I'm going to move my protractor over, and I'm going to draw another line of 2 inches at 45 degrees. So like that. Okay, so now there this is how it's represented. I've got my degrees, my distance, degrees, and distance. I've got a number that represents the shape of this line, which is going to be my proposed solution for an antenna. And I can represent it in different ways. Down here, I've got kind of pairs of numbers separated by commas and any number of them in a list. So I've got the dot dots to show there could be more. We'll just demonstrate with 2 because otherwise it's hard to fit on the screen and stuff. Okay, so based on our definitions, what is 90, 5, 45, 2? So you should have a thing up here so you can participate. And leave this up because we'll be giving away a shirt here at the end of things. And I'll put the link in here in case somebody wants that. And I would encourage you to participate because I think a lot of this stuff, well, I know for me, I was going through a video series, training series the other day, and it was great. I was getting lots out of it and stuff. But then I discovered there was a workbook that would ask you a question after every 20 minutes or so in the video series. And I started using that, and I discovered that there were lots of things that I was kind of understood, but it really helped me understand it. So that's the purpose of these things. Just make sure we're getting a chance to interact with this so it sticks more and we can kind of clarify our understanding. Okay, so we have 30 people done so far. There should be a link there. And if for some reason you can't get to this, I think some computers block it. If you just go to slido.com and type in that number, it will let you do this. And another reason to keep this up is we're going to do something at the end. I'm going to give away one of our hoodies here. We value face-to-face communication. Turn your video on. So it's another reason to get your practice in and make sure it's up if you want to try to win a sweatshirt here. Okay, let's see what we have. So yes, based on our definition, the 90, 5, 45, 2 is a chromosome. It represents a proposed solution. The genetic operator would be a way that we're going to modify the solution, which we're going to do in just a second. And then the fitness is how well it scores. But this is great. Thank you for participating. It's not a big deal if you guess the wrong thing. That's just fine. That's how we remember stuff. Okay, so here we are, optimizing the antenna wire. So now let's look at the genetic operations. So down here we've got our chromosome. And here's some different operations we could do. We could mutate the numbers. We could add random numbers to the end of it, maybe make a longer antenna. We could crossbreed it. We could get some other random ones and try to cross them. Although, since we haven't measured the fitness, we don't really have enough information to know if will be a good or bad thing. So that one's probably out. But for our purposes here, we're just going to mutate it. So here we have a mutation machine, right? This is our magic mutation machine. And we're going to take these numbers and we're going to run it into it. In reality, this would be some type of function. And then it's going to spit out on the other side a mutated version. So let's look at this and see what we actually did. Okay, first we had down over there, we've got a 90 degrees and then 5 inches. And we reduced that to 80. So it's 80 degrees now. And then we had 45, but now we've got 180 degrees. So it's going to be straight down. And then 2. So it just modified the angles on the 2 of these in this mutation machine. So if we take that and draw it, it'll look something like this. So now we have a population of 2 chromosomes that represent different proposed solutions to the shape of this antenna. So I've got two different proposed solutions. So what do we call these 2 candidates? I may have given it away, but are those 2 candidates the fitness function? Are they the genetic operators? Or are they the population? How would you describe it? And like I said, there's no penalty for guessing here. Our goal is just try to interact with this. So we've kind of got to get more experience interacting with the terminology. And the link is still there in the chat if you want to use that, or you can use the QR code if that's easier. And once again, I see we usually have lots more people on than are actually participating. I would encourage you to participate. You'll get more out of it, and you'll be ready to win the hoodie. Okay, give it just a few more seconds there. What do we call these 2 candidates? And these candidates are the population, right? Because it's the set of proposed solutions. Now, the genetic operators, this is great because we get a chance to kind of talk through this. The genetic operators, we used a mutation machine as the genetic operator just to randomly change the number. So that was the genetic operator. We took these things and mutated them in some way. The fitness function, which we'll look at in a minute, is how we're going to tell how fit they are for the purpose. Okay, so how can we tell which is better? So we've got these two things. What would be the generic name for the way to tell which one of these is better? Would it be a chromosome function, a fitness function, a genetic operation function, or ask the magic 8-ball? So while you're filling that out, I was working at a hospital as a the network administrator many years ago. And one of the analysts that was working there was starting to do some stuff with Visual Basic and having fun with it. And he made a magic 8-ball. And it was great. You could ask it a question, hit the button, and it would say yes, no, or a couple other answers. But the answer it normally came up with was ask Fritz. Because Fritz was another analyst that worked across from this guy. So you hit the button, shake the magic 8-ball, and the answer was go ask Fritz. Okay, so how can we tell which one is better? And it would be the fitness function, right? The fitness function is how we figure out how fit a particular proposed solution is toward whatever goal it is that we're trying to achieve. Chromosome function just made up, so that one sounds pretty good. Genetic operation function, that probably would be the mutate function. Excuse me, mutate function we just did. So anyway, but the fitness function is what we're looking for. How fit is this toward the solution? And I'm disappointed to see no one voted for Ask the Magic 8-ball, but I'll try to sneak that one in again sometime. Okay, so here we are. We're optimizing the antenna wire. We have two proposed solutions, and we're going to run these through the fitness function. Now, these fitness functions do the exact same thing. I'm just putting them both up here so you can see it. So we stick this one in. It goes in. Magic happens. And out the other side comes a number saying for this particular proposed solution, the value is 47. Now, that could mean all kinds of things. In this case, we're going to assume that higher numbers better represent what we're trying to do. So let's run this one through. It goes in, magic happens, and it comes out the other side. And now we've got another that solution has a 39. So in our definition here, we're trying to optimize for higher numbers. So we've got two numbers there. And the fitness function, we're representing it just as magic. It could be as complex as standing up a simulation, a physics simulator, and checking to see what the radio waves would do in these particular circumstances, which would probably be about right for the antenna. It can be as simple as, and what we're going to show you in a minute, going through and comparing pixel by pixel, two things, and giving it a 1 point if the pixels match, and 0 points if the pixels don't match. Okay, so which one should we start with for the next iteration, right? We've got these two. We said this one over here, the one over on, let's see, is that going to be the left, has a score of 45. The one over here at 39. So which one would we want to start with for the next mutation? And keep in mind what we're doing here, we're just dealing with a population of 2. We could have 10 different things up here if we wanted to. We're doing this just really simple to make it easy to understand what's happening. And yes, we would want to probably start with a 45 because we've defined that 45 is better than 39 in this particular situation. Now, we could be, if we were using the antenna to somehow measure how much of a loss there was, maybe a higher number would be worse, and we actually want a lower number. But my point is that these definitions depend on the domain, right? It's not like there's a certain way that this works. We have to understand what our domain is, and the fitness function is going to be used, but we have to understand the context. Okay, so yes, that's what we do. So we could then we could then take this and take that one. So we'd probably want to start with the one that was 45 again. We already did it once. Let's mutate it again. Let's see if we can get something higher than 45. And doing that process over and over and over again until we finally get to a point where we feel the chances of it improving are low enough that we either need to stop or we need to use different type of genetic operation for it. For example, early on, we might want functions that or a mutation function that changes lots of things. But as it starts getting refined, we may find that we need smaller changes because the big changes hurt as much as they help or something. I'll show you some examples of that later. Okay, so this wasn't an entirely hypothetical example. This particular thing is kind of hard to see, I realize, but there was a Space Technology 5 mission that involved a bunch of very small satellites that they launched into orbit. And if you see, that scale across the bottom is centimeters. So this thing is really, really small. But this was developed with an algorithm very similar to what we just went to. where they went through and they tried different things, created different solution candidates, ran it through some type of simulator to see how it would work, and came out with this crazy shape that no sane engineer would probably come up with on their own. Like, if you tell an engineer, design me the perfect antenna, they're probably not going to come up with like, well, let's use this crazy shape. But this was an example of something that used a genetic algorithm in order to optimize the shape of this antenna within whatever constraints they were working with, and came up with a solution that we probably would not have come up with as humans just trying to design it. So that's an example of this actually being used in the real world. And I don't have a lot of details on what this was doing other than the fact that they were trying to optimize for a very, very small space, since it was a really, really small satellite. And I think they communicated with each other. And for some reason, because of physics, that particular shape worked better than the other options they had available to them. Okay, so now we're going to switch into, and I'm going to show you the genetic algorithm that I made, and we're going to talk about drawing a picture of, looking closer to Abraham Lincoln. But for now, a word from our sponsors. So let's switch over. So some word sponsors, self-promotion here. If you've been coming to these, and you may be familiar with this already, but my company is called Xeric Corporation. We do a lot of stuff in kind of embedded team coaching, working with companies, working with teams, particularly coming in and working with teams, helping coach by working side by side with developers, doing development, helping practice extreme programming practices, doing a lot of hands-on test-driven development, and really helping teams get the cultural knowledge they need to be really, really successful. That's one of the big things that I've been doing over the last 10, well, it's more than that, I guess 14, 15 years now. Also sometimes coming in, just doing team augmentation, helping in areas where they just need more help getting things done. As another developer, we've got people on that work for me that are usually doing that role. We also sometimes do turnkey software projects where we've, particularly for a startup, that's like, we need an ERP system that does stuff where we're bovine genetics, and there's, you can't just drop Salesforce into something like that or some other ERP, SAP, and get it to work. So we've built some of those things out for people, particularly being able to focus with them on really delivering the business values early on and having those conversations about how to keep the business afloat financially. Because if you're just starting out, the last thing you want to do is launch into a 5-year software project, and by the time the software is finished, the company's been out of business for 4 years. I also do workshop talks and training. Internal conference speakers. Sometimes organizations are having internal conferences, and I'll come in and give talks for that. Also, something we've done a little bit of that's been fairly helpful to people is weekly coaching sessions where people are wanting, hey, we're struggling with this aspect of the business. We'd like to get an hour of your time every week to kind of talk through, here's where things are at. What are some ideas, and just work one-on-one or in small groups of just trying to help the business find good ways to move forward using agile principles, using good software development techniques, and just how to work with people in the technology space. So that's another thing that my company does. If any of those things sound interesting, feel free to reach out. You can also reply to pretty much anything I've sent you, and it should come back to me, but I'd love to talk to you about stuff. And, okay, yes. So the question, to let us interact around this, because I want you to remember this stuff, right? If you had unlimited budget, what way would you most like Mark Shead to work with your company? So as embedded, teach coaching, work daily with your, that should have been tech coaching, do workshop or training, speak in internal conference, and you can select multiple things. I just kind of want to see where we end up with on some of these things here. Did I have more stuff hidden at the bottom? Can't remember. Okay. I'll wait till we just get a few more answers. Just want to make sure you guys are thinking about that. And if any of this is interesting, please do reach out, because I would love to talk to you about. My goal here is to always work with companies where we can be very, very efficient in the way that we're working with them. So I've kind of got a large thing of have lots of lunch and learns. So throw a very, very wide net with the idea that there'll just be a few people that like, this is a perfect solution for us, that reach out, that we move forward with. So if any of that sounds interesting, I would love to talk to you. Don't hesitate to reach out. Like I said, my number's there. Just send me an email. Love to chat. Okay, back to Abraham Lincoln. Okay, so in this case, we're going to be dealing with a chromosome that represents just taking a bunch of lines and randomly throwing them down on a page. Okay, so think of pickup sticks and you take 200 pickup sticks and throw it down on a page, and when you throw it, they get to random lengths, right? You throw it all down on the page, and then you say, how close do all these pickup sticks look to Abraham Lincoln? Well, in the process I did here, this is after 50,000 iterations of taking sticks and throwing them at the page, and then taking a small number of them back and throwing them at the page and saying, was that better or worse? And just keep doing it. Okay, now, this probably looks more like a Muppet version that's starting to look like Abraham Lincoln here. We've got this random line over here. He's having a really bad hair day, but you're starting to see a little bit of the semblance come out. You can see that there's a little bit of a shape of a head, a little bit of shape of the neck, the dark at the bottom. Let's go back. So the dark at the bottom here is kind of starting to be represented there. And this was with 50,000 iterations of walking through this. And a little bit, I'll actually run this for you. It takes a long, I think on my computer it's taking about 50,000 iteration takes overnight to run. So we'll look at how that progressed. And one thing I discovered with this is the speed of your fitness function sometimes, or at least in this case, is the thing that determines how much you're actually able to do. Okay, so let's talk through the functions here. And don't worry if you don't, this is written in Racket. Don't worry if you don't understand it. I want you to just see the name of the function so you kind of understand what's happening. So that first thing on line 87, see where it says define, and then there's fitness of pixel. That's the name of the function. And then there's all the inputs that we give it. So I've got a fitness function that lets me say, what is the pixel at point at x coordinate 5 and y coordinate 6 or something like that. And what's the fitness of that pixel? And what we do is we look at the picture of Abraham Lincoln, and we look at the picture that we threw all the things down, and we say, is this the same color? And if it's the same color, we give ourselves 1 point. If it's not the same color, we give ourselves 0 points. And we just go through that. And if you see, then there's two other, the 92 and 96 are getting the color of the target. So what we're trying to, so the picture of Abraham Lincoln, and then getting the one of the of our proposed candidate. And then down here at the bottom, what we're actually doing here is, this is the logic that just says, go all the way across, comparing every pixel. When you get to the end, go down and start at the next row. Go all the way across, and keep on going. And then when you get to the end, stop. Oh, and as you're doing it, keep adding up that number and give me that number back when you're through. So it's really simple. We're just going across, counting the number of pixels that match, and then at the end, we give that back to whoever called us. So that's the fitness function. And the thing I want to call out here is this, I mean, even if you're not understanding what's happening in here, this is pretty simple, right? There's not a lot of lines of code here just to go through and say, compare this stuff. So the fitness function doesn't necessarily have to be super complex. Now, in this case, the thing that slows it down is the fact that we're interacting with the graphics layer. And Racket does some really cool things of being easy to code. If we started getting into OpenGL and some stuff like that, we could probably do things a lot faster. But this worked well because I could do it with a small amount of code, and that's what I was interested in doing. Okay, so there's the fitness function. Now let's look at the mutation function. So if you look right here, I'm not sure where there's a random line in that, but 28, we've got a method that just says create random line coordinates. So what that's going to do, and if you see on 29, 30, 31, 32, it's got random, it's just going to create a random number that's constrained by the height and width. So I'm going to get 4 numbers that fit within the height and width of our canvas that we're working with, which will give me 2 points for the starting point and 2 points for the end. Yes, the line mutated in the screen. I'm not sure how that happened. I think I took a screenshot of something that had an arrow pointing to something else and didn't realize it till I got here. But I can create a random line just calling that. Well, down here, I've got the mutate DNA. And if you notice 132, it says mutate where the rate is 0 to 1,000. So if I put 1,000 in, then that means that as I'm generating the random number, anything that's under 1,000 will mutate for each time I go through each of these lines. So that would mutate everything. If I put in 500, it'll be 50%. Now, I had started this out from 0 to 100, but I discovered that I needed more granularity because sometimes you don't want to mutate. If you're mutating 1% of things and there's 200 lines, that may be more than what you want. So that's why there's more granularity. And what this does is it goes through, there's a con there, so there's different things they can do. First, it's going to check to see if I'm done. If I'm done, I'm going to stop. That's what's happening on line 133. Then I'm going to say, okay, go ahead and create a random number and see if I'm going to mutate this time. If I do, then I'm going to do the mutation, which is for this line, throw that line away and randomly generate another line. And then line 36 is if I decide not to mutate, just keep on going, keep working your way through. And don't worry about the details behind that, but that's what it's doing. But it's fairly simple what's happening here. If you saw this expressed in a language that you're familiar with, this wouldn't be there's no magic happening here. It's a very simple step-by-step. And so like here at the bottom, let's look at with something simple. So in this case, I've got a line that's 1, 1, 1, 1. So these would all just be points, right? 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, 4, 4, 4, 4. And I'm going to say there's a 50% chance, so 500 out of 1,000 chance that I'm going to mutate. And if I run this, I end up with this. And in this case, it only mutated 25% of them because it's random. And so those first numbers, the ones got replaced with a new line that's just random numbers. It's going to be somewhere very different than where it was before. Let's see. Okay, so here's the picture of Abraham Lincoln, and one thing I discovered early on is with 250 by 250 pixels, it took a while, or I was starting with 500 by 500. Well, because the fitness function takes a while to run, that was taking a very long time. So I reduced it down to 250 by 250, and this particular image I've made black and white instead of grayscale because that's what we're working with, is black and white. So at that point, okay, so here I want to show you the demo. So here is that picture again of what happened when we started with 50,000. So we had 50,000 people, or not people, we had 50,000 iterations. So let me bring this up here. So here's the program. Oh, I guess I left it running, but that's fine. So if you notice here, see, we're just trying random things. And over here on the right, whenever you see a star, that means we got something that was better than what we had before. So it means we mutated in a way that was better. I've been running this since about an hour before we started. And if you notice, it looks significantly better already than the one we just looked at. I mean, it's still a mess, but we are seeing some improvements. So if you notice here, so this is just going to keep on running, and it would probably finish sometime around tomorrow at 10 o'clock if we let it run all the way here. Let me stop it for just a second here. Okay, so there, right now, let's see it. Okay, so there's our image. And this is just all the code that we kind of looked through. But if I scroll up through here, let's find an example of what happened. So so we're running it 50,000 times. So that's how many times it's going to remain. Then we've got our current fitness function. So the one that is our current best one was 39,522 pixels matched. And so we threw these random sticks down in a different way, random lines down, and we ended up with something that had 39,545. So that was better. So in this case, we put a star by it just to call it out. And the next time we started, we're now dealing with a current fitness that's better. We made a small improvement. It's not very much, but a small improvement. And if we keep on running this, the picture gets better and better and better. So let's see. Does that make sense? So I want to ask, does that kind of make sense what this is doing? Can you leverage matrices in your fitness function to improve the speed? So I'm not sure how we could get away from going over every single pixel other than if we looked at groups of pixels. But you may know some math that I don't know, Vince, that I'd be very interested in, because if there is a way to do that, I'm not sure how that would work, but that sounds pretty interesting. One way that I think we could possibly do it, and maybe this is what you're saying, is I'm actually drawing this to the screen. It might be easier for me to just calculate the pixels and load it all up into memory and just go through looking pixel by pixel instead of actually trying to access the screen. That might actually make it faster. But what I like about this is I understand what's happening. I can see what's happening with this. And for my purposes of understanding how genetic algorithms work, it's perfect. So, but yes, there are definitely some things we could do to speed it up. Like I said, this the graphics library I'm using is not necessarily optimized for speed. But if you do have if you want to explain on the matrix stuff later on, I would love to hear what you're suggesting. Okay, so let's go back and let's look at how this looked over time, because I don't want everybody to have to watch this for as long as it took to actually do these. Okay, play from current slide. There we go. Okay, so that's what the code looks like. So here's our picture, and this was about 50,000 iterations. Yes, we are redrawing all the lines every iteration. I don't have a way to delete lines, but I think the drawing is pretty fast. I think it's actually the comparison that's slow. So this is after 50,000. This is after 100,000. I think this is 200 or 150. I can't remember. And then like 500. I think this is 750. Maybe a million. Or maybe that one's a million. Anyway, we get to here, and I think that's 1.2 million. I should put what it was there. So now we're really starting to see, it's starting to look more like Abraham Lincoln. If we ran this for another, well, if we ran this exact same thing for another million times, I'm not sure we'd see much improvement. But if we modify our algorithm to make smaller changes, I think we can probably get more and more looking like Abraham Lincoln. I'd like to try it with polygons and maybe more lines at some point, or even dots or circles or something like that. But you can see how it is starting to evolve to look more and more like Abraham Lincoln. And one thing I think found particularly interesting here, is watch right. Okay, so right here, notice there's no mouth. And at some point, it randomly got something in there that kind of represents the mouth. And then it moved it over a little bit, got it over a little bit more. And now we've got kind of that line there representing where his mouth kind of is. I think that's the line, or maybe it's his bottom lip. But I thought that was an interesting feature to see that kind of show up. We also see how his hair kind of sticks out. Well, his hair is doing the same thing mine is right now, isn't it? His hair kind of sticks out right there. We're starting to kind of see that show up. There's the ear in the side of his head that's kind of represented on the side. And the thing I find really interesting is if you look at, particularly on the left-hand side, the way the neck has created a curve from all the lines. I thought that was pretty interesting how it got those into the place that we've got the outline of where the neck is, even though there's white in the center of it and stuff. Now, a couple comments kind of about this is the more fit something becomes, the more diminishing returns there are. Because if let's say I'm randomly changing 10% or 20% of the lines. Well, when the lines were just random, that had a reasonable chance of actually getting put down in a way that would look more like Abraham Lincoln. But when I get to the point that it looks like this, if I randomly change 10 of those lines, there's a really, really high chance that most of them, or a large percentage of them, are going to do more damage than they do good. I'm sorry, what? Let me mute everybody here real fast, just as a courtesy. Okay, cool. You get diminishing returns, meaning it takes longer for there to be to make improvements. But one of the reasons it takes longer is because mutations have just as much. If you're dealing with something that's already fairly fit, the mutations can start to have more chance of moving something that's helping you than moving a line that's helping you to a place that it's hurting you, than moving something that's hurting you to a place that it's helping you. So because of that, you may want to look at different mutations. And this is something I did at some point. I started saying, okay, instead of just grabbing 10% of the lines and then throwing them down and letting them be random again, I started just working with the endpoints and moving them by a few pixels. And I started seeing lots more chances of improvements. So now it was very small improvements, but we were iterating faster. And I'd love to take this and run it on 2 parallel computers and just let it run for 2 or 3 weeks and see if the small improvements that seemed like more likely to be helpful would come out ahead, or if you're still better off just doing the random. But I know for me, when I'm watching this run for 2 or 3 days, not seeing that star every show up starts being discouraging. So different mutation strategies, and I think this is something that if you're wanting to employ this, you need to be thinking in terms of, if you need it to be highly optimized, you need to think about how your mutation strategy may need to be refined or kind of narrow in. And if I go so long without seeing any improvement, maybe I keep on running the same thing, but with making fewer changes each time till you get down to, so you're always optimizing the process as well. So the higher the fitness of a candidate chromosome, the more likely the mutation will be harmful instead of helpful. We eventually just started moving the line ends by a few pixels each iteration, and that seemed to get a little bit more, it seemed like we were able to make more progress that way. The cost of the fitness, I mentioned that this is often the constraining factor that determines how long each iteration takes. And my my fitness function here doesn't take that long, but imagine you're standing up a physics engine to measure the radio interference between things. Depending on how complex the simulation is, that could be very, very significant amount of time for doing things. We could also look at doing parallel evolution, which would be maybe a case where we could run on different machines and then brought together to either choose the best solution or to breed solutions. So we could send a chromosome out to 10 machines, let them run for an hour, and then take the best one and then distribute it back out to all the 10 machines and let them run. And there's different strategies you can use for that. You could also take them and take the top ones and then mix them together in some way, like take every other one or somehow combine them in order to try to get the traits from each one. Okay, so that is the introduction to genetic algorithms. I hope that's useful to kind of a way to think of it, and I don't think it wasn't super technical, but I think you probably, if you're a developer, you probably know enough to actually go and try to build something like this. If you're not a developer, you should know enough to at least join the conversation. If you're working with a team that's looking at using a genetic algorithm, you should understand kind of how things are working. Okay, so, and Jason evidently had a master's class in this, so you can ask him if I got anything wrong in this. Hopefully we're at least headed in the right direction. So now what we're going to do is give away one of these shirts. I think I do not have any mediums. So as long as you will fit a size that's not medium, I've got, I think, smalls. Yes, smalls through XXX large, I think. So going to give away one of these shirts. I hope you like it. They're nice and warm, and it was very cold out today, which is why I put this on. And so hopefully we'll get one to you, and you'll be able to make use of it as well. And if you really need a medium, I think I do have a t-shirt too. So everybody join, and we will go through some of the questions from here. Okay, yeah, Vince, I think I see what you're saying. Part of the way I kept it simple, though, is I'm drawing lines on a canvas. And by doing that, I don't necessarily have a record of where every pixel in that line is. The graphic engine is taking care of that. But I think you're right. If I could represent those in a matrix instead of representing in the graph, if I didn't have to deal with the graphics engine, I think it would speed it up significantly. So that's a good idea, and that's kind of what I was saying is I skipped the graphic engine. So that's a very good idea, and I may keep playing with it, or I might find something else that's more fun to do. Having it a little slower where I can see it works better for me understanding what's going on. But that's a very good idea. And I think if I switch to a different graphics engine, I may be able to do what you're talking about more rapidly. But yeah, good thought. Okay, we'll give it a few more seconds here to join. 5, 4. These shirts are really soft and comfy, so I'd really encourage you to join. We got lots of people that aren't joining, but these are really, really good shirts. Maverick, let me put this here one more time just to make sure no one misses out. Of course, if fewer people, every person in has a higher chance of winning, right? Okay, so give it 4 more seconds. 3, 2, 1. Okay, first question. What happens as the solution becomes more fit? And read the questions carefully, all the answers. They're more likely to be harmful. It takes longer to see an improvement. You may want to lower the mutation rate, or all of the above. And the answer is yes, all of the above, which means if you answered any of them, you were technically correct. You weren't wrong on none of the answers were wrong, but the correct answer here is all of the above. Okay, who do we have? Our leaderboard looks like we've got Lucas, followed by John, Terrence, David, and Jake. Next question. What do we call a candidate solution? Do we call the candidate solution a genetic operator, a fitness function, a chromosome, or a biological agent? I'll give you a hint, it's not a biological agent. Not sure what a biological agent is. It sounds like some type of warfare. And yes, we do. We call it a chromosome. So that string of numbers that represents a candidate solution is what we're calling a chromosome. Now, you may see, if you notice my code, I referred to it as DNA. DNA is what makes up a chromosome. You could also maybe call it a gene or a genotype. You may see those words used. But chromosome, I think, from the reading I did, and Jason, tell me if I've got this right, but the reading I did, I think chromosome may be the most accurate way to represent it. But you'll probably see it called other things as well. Okay, John's in the top spot, followed by Lucas, Tom, Jake, and Terrence. Next question. What determines how well a candidate chromosome represents the target solution? Is it the mutation function, the genetic operator, the fitness function, or a protractor? So what do we use to decide how well a candidate chromosome represents a target solution? And yes, it is the fitness function. So the mutation function is the thing that actually, messes with stuff to see if we can make it better. The genetic operator is also, a mutation function is a genetic operator, so those are kind of similar. But the fitness function is the thing that we actually feed it to, and it comes back and says, hey, you got a score of 52, or whatever the number is, so you can compare it with different things and see what is more fit. And John, still in top spot, followed by Lucas, Jake, Tom, Terrence. What do we call a set of chromosomes that represent different proposed candidates? So we've got a bunch of chromosomes that represents different things. In our case, we're generally dealing with 2. What do we call that grouping of proposed candidates that represent as chromosomes? And yes, we call that a population. That's the population. And we were dealing just with 2, but in some genetic algorithms, you might create a huge population that are developed in different ways, take the best ones, and then farm those out or combine them in different ways. Like if you were trying to breed rabbits with a particular trait, you'd have the population of rabbits, then you'd be selecting certain ones and then breeding them in different ways to try to get rabbits in a particular, I don't know what you might want with rabbits, floppy ears, I guess, or something like that, or spots, I don't know, whatever. Okay, we've got John in the top space, followed by Lucas, Tom, Terrence, and Jake. Last question, I think. Which was not one of the genetic operations mentioned? Was it mutation, spin the bottle, adding random additional data, or crossbreeding? Which was not one of the genetic operations mentioned? And yes, spin the bottle was one that we did not mention. Although I could think of a way how you might come up with one called spin the bottle, but that's not one that we mentioned. The crossbreeding is one that we didn't do, but we did mention that is a way of combining chromosomes to try to get close or try to get a better fit. Okay, so looks like Lucas got the top spot. Very good, Lucas. Do you actually have one of these shirts already? One of the hoodies?
Sorry, me and Saxon. I got the shirt. I don't have a hoodie, and considering the
Oh,
Missouri cold right now, it would be pretty nice.
great. Okay. Well, send me your address and your size. I've got everything except for a medium, and we will get one. If it's snowing out there like it is down here, I hope you can put it to good use. Okay. Well, thank you all for coming. I hope that was useful. I'm going to stick around if you've got any questions, comments. I'd love to hear what people thought of this. This was more technical than some of our other things, but hopefully simple enough to still be interesting. So yeah, I'll stop the streaming here and love to hear what you think. And thank you so much for coming.